Hello, Mr. Betts here. I want to go through a variety of examples where we are using antiderivatives to evaluate definite integrals. So in this first example here, we want to take the antiderivative of x cubed. I'm going to use the reverse of the power rule. So keep in mind, if we were taking the derivative of something like x cubed, the exponent would go out front. So we multiply by the exponent, and then we decrease the exponent by 1. So the reverse, we're going to increase the exponent by 1 and then divide by the new exponent. You can also just check your work here by reversing this and take the derivative. So if we take the derivative of that, we should get that. And it's a quick, easy way to check that we did it correctly. Then we're going to evaluate this from 2 to 5. So we're going to get 5 to the 4th over 4 minus 2 to the 4th over 4. And simplifying, we get 625 over 4 minus, 16 over 4, which is, looks like it's going to be 609 over 4. You could, if you're simplifying using a calculator, you could, write that as a decimal. This would probably be a non-calculator question, but the simplifying is not the important part. The notation that we're using here and then evaluating is what I'm focused on right now. In the second example, we want to take the antiderivative of the sine function. So the antiderivative of sine is going to involve cosine. A common mistake is to say the antiderivative of sine is cosine, but that's the derivative of sine. Keep in mind that if we take the derivative of cosine, we get negative sine, or the opposite of sine. So I'm going to put that opposite, or the negative, in front. So we're going to evaluate that from 0 to pi. So we have the opposite of cosine of pi minus the opposite of cosine of 0. Cosine of pi is -1. The opposite of that is +1. And then cosine of 0 is 1, so this is going to be 2. This is kind of an interesting result, I think. If we were to graph the sine function, this area between 0 and pi is exactly 2. So it seems kind of crazy that that area under the curve of sine is such a simple answer. Next example, we have the square root function. With the square root function, we can think of this as x to the 1/2. So then we can apply the power rule to this. So the antiderivative, we increase the power by 1. So it's going to be x to the 3/2. And then we divide by the new power, so divided by 3/2. To avoid a complex fraction, what I like to do is multiply by the reciprocal. So instead of dividing by 3/2, we multiply by 2/3. And as I mentioned before, we can confirm that is an antiderivative by taking the derivative and showing that we get the square root of x to begin with. Then we're evaluating this from 1 to 9. So we're going to have 2/3 times 9 to the 3/2 power minus 2/3 times 1 to the 3/2 power. Now, 1 to the 3/2, that's pretty easy, I think. 9 to the 3/2, remember this is the same thing as, we could say 9 to the 1/2 to the 3rd power. We could say 9 to the 3rd power to the 1/2. So I'm going to write both of those out here. The 1/2 is a square root. If I'm doing this without a calculator, I like this better than this because we can take the square root and then cube it rather than cubing it and then taking the square root. So 9 cubed is a very large number, and then taking the square root, that's kind of annoying. So if we take the square root first and then cube it, that's a lot easier. So square root of 9 is 3. 3 cubed is 27. So we have 2/3 times 27. I'm going to factor out that 2/3 because that's going to make simplifying a little easier. Minus 2/3 times 1. So that's 26. So we're going to have 52/3. Last example, the derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And then we're evaluating that from 0 to pi. I want to point out that a common mistake here, and this is a mistake, is to say that this is the tangent of x. We are not using the variable x here. Make sure that you use the variable that's in the problem. So in this case, we have The antiderivative of secant squared of theta is tangent of theta. I also want to point out, just a refresher about definite integrals, is that this differential here tells us what the horizontal axis is, and it tells us that these are values of theta. So if we were to change this to tangent of x evaluated from theta equals 0 to theta equals pi, we've kind of, changed the problem, and that's not something we could actually do. So anyway, we have the tangent of pi minus the tangent of 0, and we've got a problem here. Probably should have mentioned this a little earlier, but if you were to graph the tangent function from 0 to pi, we're going to be jumping over a discontinuity. And more importantly, it's actually an infinite discontinuity at pi over 2. Well, this is something that we don't think of a whole lot, but the fundamental theorem of calculus says this works as long as the function is continuous. Well, this is not a continuous function, and so we can get around that using a piecewise function and essentially splitting it up at the discontinuity. So let me start this over here and do this a little bit better. So 0 to pi over 2 of secant squared plus the integral from pi over 2 to pi of secant squared. Now, before I go any further, I'm going to tell you that we can't do this. And we can't do this because if we're evaluating this one right here, this is going to be an area that is unbounded above, and we don't know how to do that. At least we don't know how to do that yet. So if we're trying to evaluate an integral where the function is approaching a vertical asymptote, we can't do it yet. That is something that we're going to do later, but like some other things that I've talked about so far, we're going to say not yet. If I change the problem a little bit here and we go from 0 to pi over 4, we don't have any problems. So secant has discontinuities at pi over 2, and really anywhere that cosine is equal to 0. But we don't have any of those on our interval here, so we're okay. So this one, we can take the antiderivative, evaluating from 0 to pi over 4. And so we get the tangent of pi over 4 minus the tangent of 0. Tangent of pi over 4, remember pi over 4 is a 45-degree angle. So if we're on a 45, 45, 90, we're doing tangent, we get 1 minus 0, which is 1. Another kind of interesting result, that this area that is kind of an irregular shape is such a simple answer.